The topic of this video will be the E1 reaction. The E1 reaction is a first-order elimination reaction. The E stands for elimination. The 1 is for unimolecular. Just like the SN1 reaction, only one molecule is involved in the rate-determining step. And just like SN1, the one molecule that is involved in the rate-determining step is the substrate. Let's look at the general reaction. Our substrate will have a good leaving group, just like it did for a substitution reaction. The difference when we're talking about elimination reactions, however, is that there must be a proton on the carbon next to the carbon with the leaving group. Therefore, the general structure of a substrate for an elimination reaction looks like this. Instead of a nucleophile, we'll use a base, because this is a deprotonation reaction. This is a Bronsted-Lowry base. The product will be an alkene plus the conjugate acid of the base plus the leaving group. The mechanism of an E1 reaction starts very much like the mechanism of an SN1 reaction. In the first step, the leaving group leaves, producing a carbocation. In the second step of an E1 mechanism, the base removes the proton adjacent to the carbocation. The electrons from the carbon-hydrogen bond form the pi bond between the carbon and the carbocation carbon, forming the alkene product. Now let's look at an example reaction. We will look at the reaction of bromocyclohexane with methanol. This reaction requires heat to form the cyclohexene product. Now let's look at the mechanism. In the first step of the mechanism, the leaving group leaves, forming the carbocation. You may find it helpful to draw in all of the hydrogens at the carbocation center as well as the neighboring carbon centers. In the next step, the base deprotonates one of the hydrogens next to the carbon that is the carbocation center. Because of the symmetry in this molecule, it doesn't matter if the proton that is removed comes from the top or the bottom. The methanol removes the proton, and the electrons involved in the bond to that proton form the pi bond to the carbocation. This produces our cyclohexene product. Just like in an N1 reaction, it is the first step of the mechanism that is slow. It is the rate-determining step. Therefore, the rate of an E1 reaction is dependent only on the concentration of the substrate. The structure of the base has no bearing on the rate of an E1 mechanism. We often see that the base is weak, and it's often the solvent. The structure of the substrate does affect the rate of the E1 reaction, and typically what we see is that the tertiary substrates react most quickly, followed by secondary, followed by primary. This follows the stability of the carbocation that is formed in the rate-determining step, just like it did with the SN1 reaction. Methyl substrates cannot react in the E1 reaction because there is no proton on a neighboring carbon to the carbon with a leaving group. Hopefully, at this point, you're noticing that there are some similarities between the E reaction and the SN1 reaction. Both of these reactions involve the formation of a carbocation, and they involve a weak base or a weak nucleophile, which are often the same thing. What this means then is that the E1 and the SN1 almost always compete, and you often get both products in such a reaction. Let's look at an example. When reacting this substrate, which is tertiary, with a weak nucleophile / weak base, such as ethanol, we will get a mixture of products. We will get both the E1 product as well as the SN1 product. Take a moment and pause the video and work through the mechanism and make sure that you can understand how both the E1 and the SN1 products are formed. Again, because E1 and SN1 both involve the formation of a carbocation, E1 reactions can experience rearrangements just like SN1 reaction. Let's look at an example. If we treat this substrate with a weak base, we will get two products. Both of these products occur from a rearrangement of the carbocation that is formed in the first step. Let's look at the mechanism. The first step of an E1 mechanism is the leaving group leaves, forming the carbocation. This is a secondary carbocation, but a hydride shift can give us the more stable tertiary carbocation. This carbocation can eliminate in one of two ways. We can remove a proton from the secondary carbon next to the carbocation center to get a left product, Or we can remove a proton from the primary carbon next to the carbocation center to give the right product. We get a mixture of these two products. However, the product on the left is the major product, and the product on the right is the minor product. This difference in the amount of the two products can be explained using Zaitsev's rule. Zaitsev's rule states that in elimination reactions, the most substituted alkene usually predominates because it is more stable.